Well, if you're like most people, you've heard of El Nino, but you're not too sure exactly what it is. Well, let's fix that. Let's learn all about El Nino. Actually, we call it INSO, El Nino Southern Oscillation. So let's just see what that's about. All right, first of all, what is El Nino? El Nino is this periodic warming of the eastern part of the Pacific Ocean. It is a characteristic of water temperature distributions in the equatorial Pacific Ocean, particularly. And during an El Nino event, there is warm water found in the eastern part near South America and North America. And El Nino events happen. It depends from year to year, but generally on a period of time from say 2 to 7 years. So every 2 to 7 years, we have an event in which we have a movement of warm water across the Pacific Ocean in an eastward direction, and we call this an El Nino event. Now, the reason we call it El Nino is because it was first observed by the fishermen in Peru. Now, Peru is an area where there is a phenomenon known as upwelling. So, what happens is in the ocean, plankton and fish and organisms that live in the pelagic or surface waters, when they die, their carcasses sink to the bottom, carrying nitrogen and phosphorus with them. So, there is an accumulation of nitrogen and phosphorus and other nutrients in the cold waters down deep below the photic zone. And what happens is in certain regions, coastal regions, especially say in Peru, there is a phenomenon in which water is brought to the surface, cold water is brought to the surface in a phenomenon known as upwelling. And so when you take these nutrient rich waters and you bring them to the surface where there's light, suddenly the productivity explodes. And so the fisheries in off the coast of Peru in most years where this upwelling is occurring are tremendous. There's just an enormous amount of productivity. So there's an enormous amount of food, and so there's a lot of great fishing. But for hundreds and hundreds of years, the Peruvians have been enjoying the benefits of this upwelling. But what they notice is every 2 to 7 years, there'll be an event where starting around Christmas time, so late December, suddenly the waters are no longer cold. Warm water comes in, there's a lot of fog, and the fishery just collapses. The fish migrate away and they're no longer catching fish. And so the Peruvians who noticed this tendency, since it happened around Christmas time, they called it El Nino, which basically means the baby boy, meaning Jesus, because he was born at Christmas time. And so that's where the name comes from. And here's how it happens. So if you recall, the trade winds, equatorial trade winds, tend to blow from east to west across the oceans. Well, the Pacific Ocean in particular is vast, and so and it's unimpeded by land masses. And so what happens is the constant flow of winds in a westerly direction caused by the trade winds causes this warm equatorial water. Being at the equator, it's well warmed. It gets dragged across the ocean, and it pools up when it reaches Australia and the archipelagos in this part of the Pacific Ocean, like say Indonesia and the Philippines and so on. And so what happens is we get this thing called the Pacific or the West Pacific Warm Pool. We just the trade winds just pile the water up here, and hang on, so much. Okay, thanks. Someone just brought me a cookie. Sorry, I got disrupted here. All right, so what happens is, ooh, it's a nice cookie too. Look at this. That looks like a good one. Almonds and white chocolate chips. Wow. Okay, now what happens is this water pools up here, and warm water has a lot of energy in it, and so it's going to change the energy distribution on the planet. It's going to change convection on the planet, and that's going to lead to climate conditions that are dependent upon this warm water being where it is. Now, so basically, the trade winds are so consistent that they literally pile the water up here. The water on the west side of the Pacific Ocean is about half a meter higher than it is in the eastern Pacific, where the upwelling is occurring. So it tends to pile up. So there's this big pool of warm water here. And it's also worth noting that warm water, being hot, the molecules move faster. So remember, anytime you heat things, they expand. So the water here is just, it occupies more space. So there's just a large volume of it over here. And this warm pool extends down to a depth of about 150 meters. So it's quite a large amount of warm water that is located in typical years, in non-El Nino years, what we call neutral condition years over here. Now, it should not be surprising then that if I have a lot of warm water, I'm going to have convection. And so what happens is warm water here heats the air. The air rises, which causes a lot of precipitation because remember, rising air is always going to lead to precipitation. But we get a convection cell established, and it's called the Walker circulation. And basically, what it does is it operates in the same direction as the trade winds. So air rises in the West Pacific. This diagram is not quite correct. It shows it going all the way across the ocean. The Walker circulation typically comes down halfway around Tahiti, uh, and you get this convection cell established. So we expect then, because of this east-west convection cell, to get warm water leads to rising air, which leads to precipitation in the western part of the Pacific, and we tend to get drier conditions in the middle and eastern part of the Pacific Ocean. Now, this Walker cell does a rather interesting thing. So, because it is rising, the air is rising in the west and sinking in the mid-Pacific, it causes the wind to move in a westward direction, which is in the same direction as the trade wind. So this Walker circulation, which is caused by this warm water pooled up here in the western Pacific near Australia and the Philippines, it strengthens the trade winds, which moves even more warm water across, which makes it even deeper and higher piled water, which increases the circulation here. And so when something like this happens, we refer to it as a positive feedback loop. And this Walker circulation cell is a good example of that. So a positive feedback loop is basically anytime I have a phenomenon in which the outcome of the phenomenon causes the phenomenon to occur more or faster. So a good example would be like if I start a small little tiny fire, I put one little spark in a pile of leaves. Well, in that one area, I'm going to release chemical energy stored in the leaves. And when I release that energy, it makes it hot. And now that heat causes more leaves to catch on fire, which makes a bigger fire, which makes more heat, which makes more leaves catch on fire, and so on. That's a positive feedback loop. Well, that's what we see with the Walker circulation. Because, no, it's not going to show us here. So what happens is, as this air rises here and sinks here, it increases the speed of the trade winds, the strength of the trade wind, which pushes more water over, which makes more deep warm water, which makes more convection, which makes stronger trade winds, which moves more warm water, which makes stronger convection, and so on. So it's a classic example of what we call a positive feedback loop. These are what we call neutral conditions. This is what we normally experience in the Pacific Ocean. Now, so the monitoring stations that first discovered this phenomenon are located in Darwin in northern Australia, which is in that warm pool area, and in Tahiti in the mid-Pacific. And so what scientists notice is in most years, because the air is rising here, this is where Darwin is located. Remember, rising air is associated with low pressure and sinking air is associated with high pressure. So what they find is in typical years, we have low pressure in Darwin where that warm pool is causing air to move upwards. And this Walker circulation tends to descend here in Tahiti. So descending air tends to be dry air and high pressure. So in most years, in neutral years, we have low pressure in Darwin, high pressure in Tahiti. But every 2 to 7 years, we have an event called the Southern Oscillation. And in the Southern Oscillation, for reasons we still don't really understand, suddenly there's a shift. And what happens is the pressure starts to increase in Darwin and decrease in Tahiti. And when that happens, it disrupts this pattern that's been established, and that triggers an El Nino event. So what happens is, here's Darwin over here. When the pressure starts to go up here and goes down in Tahiti, suddenly there's this reversal in the direction of the wind. So whereas the Walker circulation used to be moving the trade winds this way, now what happens is I have actual a movement in the opposite direction. The trade winds in the Western Pacific not only weaken, they sometimes reverse themselves and they start blowing to the east instead of to the west. And over here, what happens is these become weaker. The trade winds over here become weaker. So what happens then is we have all this warm water piled up near Darwin, And what happens is suddenly the winds are starting to blow it back across the ocean. So now as this warm water moves across, now these convection patterns are shifting, and the circulation patterns associated with them are shifting, and this causes what we call El Nino. As this warm water moves across, the upwelling on the coast of the Americas stops. The fish move away. The fishermen in Peru are sad, and the weather across the planet is unusual, and we call this an El Nino event. Let's see, we just talked about that. So what happens ultimately here is a good diagram of it. What happens here is warm water, which was here, now is moved across because the low pressure is located here in Tahiti with high pressure in Darwin. So the air is circulating this way now in the Walker cell, which causes the movement of water across, and it basically pushes this water across. And don't forget, the water over here is higher than it is over here. So now what happens is it's just basically flowing back downhill, and the warm water ends up here. And some of the consequences of this are global in scale. Now, here's just a good comparison. Under normal conditions, the warm pool is located here because the trade winds are blowing the warm water across the equator to here. But during El Nino, southern oscillation events, the winds are blowing in the opposite direction. So the water moves back across, and now I have warm water here and a cessation of the upwelling. Now, so here's what normal conditions would look like. So these images that we get from satellites, they can get these images in a number of ways. One is you can simply use like what we use here at KS when you walk in the morning, it takes your temperature. We can put satellites into place that are able to monitor the temperature of the ocean surface by looking at infrared light, just like what happens when you walk into KS in the morning. Another thing we can do is we can send lasers down and record how long it takes that pulse to come back up and use that to determine the height of the water. So remember, warm water is big, it expands. So where the warm water is, the sea level is a little bit higher, and so it would take less time for that laser beam to be reflected off of this part of the ocean than it will off of this part of the ocean because it's traveling less distance. And believe it or not, that even though we could be talking about just centimeters of difference, our technology allows us to detect that. And so we find is during El Nino conditions, this warm water that's pulled up here leaks back across, and it starts covering the areas here. And I don't know if this is the best picture ever, but it shows basically when you see this warm water across the equatorial Pacific, that's when you've got El Nino conditions. So the Walker cell normally is rising near Darwin because the warm pool is located here and sinking around Tahiti. And we get this pattern here, which creates a positive feedback loop because the circulation of the east-west circulation of the Walker cell is augmenting the normal Hadley cell circulation patterns of the trade winds. And so these two circulation patterns together are strengthening the flow of air westward across the Pacific, which drags more warm water to the warm pool. So it's a positive feedback loop. Now, what I like about this diagram is it shows you the other, as you go across the globe, you can see where other circulation patterns exist and where we'd expect to have rain conditions. Now, watch what happens when we move from neutral conditions to El Nino conditions. Now, in El Nino conditions, notice in the mid-Pacific, we have this rising conditions where we got a lot of precipitation here. And so what's happened then is we're not getting precipitation here in Southeast Asia and Northern Australia. So during El Nino, we would expect to get drought conditions in Southeast Asia and Australia. And notice what happens is it leads to a strengthening of this particular convection cell. So we tend to get floods in this part of East Africa. We also tend to get floods here in South America because of all the warm water causing local climate disturbances. So let's take a close look at this because this is showing us things you're going to need to know for the test. Okay, so basically, during a strong El Nino condition, here's our warm water. We see it moving across the Pacific. It was here. It's now moved here. So what are some of the consequences? Well, one thing is let's look at where we're going to have wetter than normal conditions. When this warm water gets here, we expect to have floods. And, that there's, when you have floods, you have erosion, you have loss of human life to flooding here, Obviously, in the middle of this, in the Tahiti area, although there's not a lot of population there, in this one part of East Africa, so in, say, Kenya and Tanzania, and then the southern United States. And let's just be real, the AP test is very Americentric, so it's worth knowing that during an El Nino year, you can expect to have a lot of wet weather in the southern United States as a consequence of this warm water movement. You'll also get drier than normal conditions clearly in the area of Southeast Asia, Darwin, because now what happens is this is what causes monsoon conditions, and now it's just not there. So we get droughts. We also get droughts in the southern part of Africa, like say in the area around Malawi and Madagascar, and drought conditions in the Amazon basin. We also get warmer than normal winters here in Korea and Japan, in Alaska, and in eastern Canada. So those are the conditions that we expect during an El Nino event when this water moves across. But wait, there's something else that could happen. First of all, let's just say these are the three things we'd get: weakening of the Asian monsoon during an El Nino, which is going to cause drought conditions in southern Africa and Australia, and high rainfall in northern Africa and the southern US and in Argentina. Now, La Nina is the opposite of El Nino. La Nina is just when this Walker circulation gets really revved up, when this positive feedback loop gets so strong, it moves so much warm water across that we start seeing this cold upwelling water starts moving across the Pacific. So we've basically taken so much warm water across that we're now starting to drag cold water across. And so it's sort of the opposite. Now, think about this. Now we've got a lot more warm water here. So what's going to be the consequences of La Nina? Well, it's going to be in a way kind of the opposite. Now I'm going to have basically, oh, here I'm going to show you this. So basically normal, and then you notice the cold water moving across. That would be La Nina rather than El Nino. More warm water here than normal. So basically higher sea levels than normal. Now, what would we expect? We'd have more rainfall than normal with the Asian monsoon. So we'd expect flooding in Southeast Asia, in India, flooding in Australia. We'll get increased rainfall in parts of Africa and Brazil, and then drier than normal conditions in the southern US, which they're going to ask about probably. And also, as you point out, when you have drought conditions, you tend to get more forest fires. All right, so that's El Nino, Inso, La Nina. I know it's a lot, but hopefully once you start working through the problem sets, it'll start to make sense.